So Spectral Color in PDF 2.0 and PDF X6. Who of you has a clear understanding about what Spectral Color is? Kind of. Somehow. Okay, let's...
Maybe it's not.
Depends on what you mean by clear, right?
It's the future.
Great.
You don't have to work in marketing. So spectral. So why would we want to think about spectral? So let's go one step back and look at how we represent color digitally so far, most of the time. So the most widely used way to use color is to use 3 numbers and assume they provide enough information to display the color, for example. So the most widely used color model still is RGB. You have 3 numbers, something that represents the red aspect of the color, the green aspect, and the blue aspect of the color. Seems to work pretty well. Last time I checked my phone, the color still looked still okay. So RGB is okay. Some people found that you want to be more specific in a certain way because just 3 numbers may not be enough. So they invented other types of 3 numbers. So let's say LAB, for example, or XYZ, which are slightly more than 3 numbers. So for an LAB value, you would still have to indicate what type of lighting you are expecting for this. So D50, for example, which is somehow equivalent to a light temperature of 5,000 Kelvin, but not exactly. So that would be a more precise way to digitally describe color. You could also continue to use RGB, but also qualify these 3 numbers by using what's called an ICC profile. So ICC profile provides additional information, provides a kind of reference to the 3 numbers. So that you mean these 3 numbers and not the other 3 numbers of the rendering. Then of course you have other. So these approaches are actually called process color models. So you use a certain amount of numbers or colorants and you combine them and you try to represent as many colors as you can using that. And the same way you could use RGB triples to express the appearance of a color, you could also use CMYK. And CMYK was only invented because printing is never perfect. Theoretically, if you blend cyan, magenta, and yellow, you will also be able to cover all colors, but especially once it turns towards gray or black, it becomes more difficult to actually produce a nice gray or nice black. So it seemed easier to just throw in a black color and use it whenever you need black. And in the colorful cases, you would rather use combinations of C and Y. So we've been using that for a long time. So for preparation of digital print files, if you go back, like let's say to the beginning of PostScript in 1984, which was pretty much black and white at that time, but they started adding color even already in PostScript 1. So let's say mid-80s, late 80s, they started using digital information to print colorful prints. And as far as I can tell, it didn't work out that badly. So you buy a magazine, you buy a book, you buy a poster, you buy something. I would say most of the time people seem to be happy. So we seem to be able to go quite far just using 3 numbers or 4 numbers in a certain way to express color appearance. And then of course there's a lot of details to be kept in mind as well, but it can be quite okay. Nonetheless, some people thought, already in the last, I would say 10, 15 years, probably 10 years, but this is not enough. We need to become more precise, more predictable, and so on. And this is especially true when it comes to more special colors. So the average photo that you take with even a good camera, you can do a pretty good job just using RGB or CMYK values and get that printed. More specific colors are colors that certain corporations, for example, care about. So IBM cares about their blue, and Coca-Cola thinks a lot about their red, and there are other companies who have other colors. And it's very important for them that the color always looks the same, so the Coca-Cola can should always have the same red, regardless where in the world we're actually getting it. And also, it should be very close to the color, it should always look the same. And that can be challenging if you print on all kinds of printing devices and offset press, digital press, this and that. It also becomes more challenging when you start mixing colors. So if you wanted to be smart and use, let's try something else. Let's try Deutsche Post Gelb, the yellow from Deutsche Post, which turns out to be a special yellow. So they have Deutsche Post yellow, of course, because they're special. And now you wanted to use that as a spot color, but you would still want to use it like a yellow, and you want to use it with cyan to create some green parts of a page. Then it turns out that it can become difficult to predict how, let's say, 50% of Deutsche Post yellow interact with 50% of process cyan. It's been done. It's happening all the time, because if you open a PDF file with 50% of a yellowish color over printing a process cyan and looking at it in Acrobat or even in Preview or just about any other viewer, it looks pretty green. So it's not completely wrong. But if you would print it on a couple of printing devices and hold it next to the rendering on screen, it might not be exactly the same as what you get out of the print. And some people care about that. So they want to be able to make more accurate predictions, especially when mixing colors, or maybe also when printing color on an unusual substrate. So normally you print on white paper or something that's pretty white. But what happens if you print it on something that's not quite white, but has it's yellowish or greenish or reddish or whatever? So just using information that is based on 3 numbers per given color doesn't give you enough information to predict what the mix of colors would look like. And there are many reasons for this. The behavior of a color when printed on the substrate is not linear. So if you print more color, let's say if you print twice as much color, it's not twice as much blue, for example. Or if you just print a 50% tone value, it may not be half blue or just a lighter blue, but lighter by 50%. It could be something else. It could be much lighter or still relatively dark. And there's also certain inks that have a different use. It's not a cold blue anymore. It turns slightly reddish. So it's just not linear. So the idea was to gather stronger information for a given color. And the approach is then what we call spectral data today. So instead of just trying to identify 3 numbers that represent that color, you try to measure spectral reflectance. What does it mean? Light, as we see it on a daily basis, is sending out energy on different wavelengths. So it goes from infrared to ultraviolet, where, strictly speaking, you can't see infrared and ultraviolet, but just the wavelengths in between. And the reason we can perceive color is because our eye receives different amounts of energy from different wavelengths. So we receive a certain amount of red, a certain amount of yellow, a certain amount of blue, and then our eyes and our brain calculates a color impression from that. So if it's mostly red and hardly anything of the other wavelengths that hit our eye, then we think it's red. And if we receive more on the other end of the continuum, like a lot of blue, then we probably perceive that as being blue. And the good thing about this richer information is that if you let's say you have a red ink, you measure it just at 100% printing, getting all kinds of energy levels at the various wavelengths, and you do the same at 90% and 80% and 60% and so on. Get much more fine-grained information. You could, for example, find out that, let's say, Coca-Cola red at 50% turns slightly orangish. Then your spectrum would reflect, there's more yellow parts in the light that gets reflected than for the other intensities. And you would also kind of be able to detect why. So in which part of the yellow spectrum is stronger and how much is it, like all of the yellow bits are slightly higher, is it just one peak and so on. And do that, let's say, for another color, like Coca-Cola red and then maybe some blue, because you will also want to print some violet. You have the same information for blue. It becomes easier to develop a model that kind of takes both pieces of information into account, like the 50% Coca-Cola yellow and the 50% Deutsche Bank or IBM blue. And then you can develop a model that, if you get it right, does the right thing, and gets a more reliable prediction of what 50% Coca-Cola red printed on 50% IBM blue will look like when you get the print out of the printing press. And it's that assumption, or in some cases it has been proven to work, that can make it worthwhile to collect spectral data and to do something with it. I know some people who have done work in this corner. So in Germany, the company GMG is pretty strong in color science, and Hanno Hofstadt, which is the main scientist in this corner, he has been working on modeling this, I think, for the last 10 years or so. And at least like 5 years ago, he was not yet happy, so sometimes it works well, and sometimes it doesn't. And I think they have made quite some progress and can get more predictable results by now than you can achieve with any other approach. Is this somehow clear so far? Kind of? More numbers, yeah. We will look at actually at some specific numbers in just a second. So let's assume this works. So I can get information about Coca-Cola red and IBM blue or whatever, or any other color I care about. In which situations could this be useful? Yeah. So just writing additional numbers in my PDF file, yeah, you can do that. But why would you care? And just to make this clear from my point of view, there's two situations where this information can be very interesting. Let's assume again the Coca-Cola can. If you print the red on the can on the printing press, then the ink is red and it will still be red when it hits the can, and if you look at it, it will still be red. So it will be highly predictable because it's the ink that controls the appearance of the ink on the can. We will not be able to get anything out of spectral data because it's the ink that's the decisive factor. Yeah, so the can will be red because the ink is red. But we wanted to know beforehand, by looking at a simulation of the print on screen or on some proof print, it would be cool if we could trust the print or the screen rendering that the red is exactly the same red as the printed ink on the can. And it's this scenario which I would call proof simulation, or print simulation if you want, but probably more proof simulation. So you don't do the actual print, you do a substitute of the print by using some proofing system, whether it's on screen or on a printing device. And it has been shown by certain vendors that you can get more accurate predictions of the appearance of that color if you use spectral information and use it during the printing process. So you kind of convert that additional spectral information about the Coca-Cola red to something that will get a more accurate rendering on screen or on the printed output piece. So that's one important situation. The other situation is, and it's becoming more relevant in the industry, So far, when printing Coca-Cola cans, they will use a printing process that has exactly that right red ink to put on the can. There are now more and more digital printing systems that don't have special ink for each of these brand colors. They rather have a set of inks that are very good at simulating just about any other color. A typical approach is to still use CMYK and then orange, green, and violet, for example. And if you mix these 7 colors in the right way, you can get many more colors than you could get out of CMYK. And you can get a much better approximation even for special colors like Coca-Cola red, which can be hard to hit if you just use CMYK. It might be difficult to hit exactly the Coca-Cola red. It might be relatively similar. But because Coca-Cola is picky and they pay a lot for the printing, they want it to be very, very accurate. So what you would do is if you take the print-ready PDF file that's normally used in, I don't know, flexo printing or whatever, and it gets you the right red because it's just the right red ink in the printing press. If you could use that information and derive back, based on spectral information, the right combination of CMYK, orange and green parts on your digital printing press, then you can probably do a better job at simulating or approximating the Coca-Cola red on your digital printing device. So that's the other important scenario. So one is simulating the expected output by doing proofing, and the other one is converting a spot color or maybe several spot colors to a combination of other inks that are available on the system you're using. So these are the 2 relevant use cases, and to the best of my knowledge, there's no other relevant use case. So if you're just printing spot colors anyway, it will not do you any good. Now, that much said, there are maybe 2 or 3 relevant standards in this field, and if you have been in the session before from Stefan Jeggi on the Drupa insights, he mentioned some of that already. So, for this type of use of spectral color data information, there's a standard, I'm showing the title page here on the screen, which is called CXF/X4. And it's a way to put information about single spot colors inside an XML file in a very specific manner. So that's an important standard in this field. It does exist independent of PDF, so you could use it in some other context as well. But PDF is probably going to be one of the major contexts where this will find the use. The principle of how information is encoded is relatively simple. So in the best possible case, you have 11 pieces of information how the spot color is printed on a white background of the substrate or the paper or whatever you're using for printing. Full color and no color, which is the substrate, and then in between steps of 10% tone value increases, so 10, 20, 30% of the ink on that substrate. And then the same again after you have printed black ink on the surface before. So full color on 100% black, 90% spot color on 100% black, and so on, all the way down to just 100% black. That's kind of the most efficient approach to this, where there's enough information to compute a model, because measurements are also expensive. If you have to measure 100 or 200 fields, it just takes longer. So the experts thought this is the right amount of information to ask for and to use. The other standard where this will become possibly relevant is the PDF standard itself, but only in version 2. So the ISO committee is still working on PDF 2.0, and we expect to finish PDF 2.0 towards the end of the year. Then there will be a final approval round, and hopefully early next year or maybe summer next year you will have an official ISO document about PDF 2.0. And it will introduce a spectral data entry in output intents. So output intents are very important for PDFX, for file exchange in the printing industry. There will be an additional entry that's called spectral data, and it will contain essentially files that comply with the CXF/X4 standard. So you can have for each and every colorant, spot colorant, in your PDFX file, you could have spectral data-based information about that spot color. So there's a
What about the spot?
good question. I've just rewritten that. Let me think. I'm not 100% sure about cyan, magenta, yellow, and black. Normally, it would not be useful because you have to have the destination profile anyway, and that's a much richer description of the CMYK colorants than you could get by spot color by spectral data.
But that means that if an image wants to use the spectral data, it has to be a UI CMYK to use the spectral information out of the output intent.
The spectral information characterizes a single color. The image is an array of many colors.
Yeah, but if it's in the output intent, it's
Let's-
for all the part.
Let's make one thing clear first. PDF objects on the page don't use spectral color.
Okay.
You can use spectral color information to do something with the content on the page. So the PDF page objects will still use device CMYK, ICC-based RGB, LEB, whatever you have. Just the normal things. And the expected rendering of the page will still be just that. Forget spectral data, even if it's present. And then, if you have the need to do a simulation of something, or to do a process conversion to something else, you can look at the spectral data and try to make some sense of it and do something with it. It's very important also to see that PDF 2.0 itself does not explain the tiniest bit about what to do with this. So the only thing you mention in an informal note is say, this data can be useful for purposes like improved or enhanced proof simulation or process conversion. We don't say you must do anything with it. We don't tell you how to do it if you're doing it. It's completely up to you. Now, this is PDF 2.0. This is a general purpose PDF standard. So it's as relevant to invoices being sent by email and to print-ready files and to fillable forms and even animated content, whatever. So PDF 2.0 itself is not too much interested in providing precise guidance for the printing industry. But we have yet another standard, PDFX, that cares a lot about the printing industry. So far, the latest development is PDFX4, which was initially released in 2008 and then updated in 2010. We're still, as an industry as a whole, we're still in the process of adopting it. There's lots of printers who still have to get up to speed using or taking advantage of PDFX4. But that's the current state of the industry if they are relatively up to date. The PDFX committee in ISO is nevertheless also working on the next version of PDFX based on PDF 2.0. And it will take advantage of a couple of new bits in PDF 2.0. So you can now have page-based output intents. So you could have one output intent for the first page, a different one for the second page, which could be interesting if you do like color printing and black and white printing inside of the same job. And there's a couple of other minor things. To be honest, nothing major, nothing that will revolutionize printing or so. There has been some discussion what to do with the spectral data entry in PDF 2.0. Is this the next big thing for printing? So maybe we do a much better job in certain areas. Should we introduce rules, what you actually should be doing with the spectral data? This is how you have to process it. And it has been the agreement in the meeting, which was just a few weeks ago in Berlin, that we will not prohibit the existence of spectral data in the X-6 file. So it's allowed, it's okay to have it. We will also not prohibit that people make use of it, but it's out of scope for the X-6 standard. You know what to do with it? Go ahead. Now this may come as a big surprise. So there's some cool new technology, why don't we take advantage of it? Because you can make better proofs and you can make better process color conversion. You have to understand this is not much different from what we have had in the past. So let's look at PDFX4. What do you know about spot color? You have Coca-Cola red in your PDFX4 file. What do you have? You probably have 3 or 4 numbers. So you may have an LAB value for the appearance of the Coca-Cola red. You may have ICC-based RGB, you may have ICC-based CMYK, something like that. 3 numbers or maybe 4. And maybe information about the light, which would normally be D50. So how do we know what 50% Coca-Cola red looks like when Acrobat renders it, when the Adobe PDF print engine renders it, when the Harlequin renders it, when it's not like sending the spot color ink to the press, but just doing some rendering and some simulation in the end. We all interpolate. It's as easy as that. So we do like this. And it works relatively well. ESCO does it, Callas does it, we all do it. Yeah. There's some refinements that you should take into account when doing this. To just using maybe CMYK colors and just doing interpolation using that may not give you the best possible results. They more often fail to match properly. But there's other stuff like you convert to X, Y, Z, and you do something and multiply and this and that. But everybody who's looked into that will have figured it out, and it's actually also relatively consistent. Does PDFX4 say anything about the alternate space of spot colors? That's how you call them, and what to do with them? I have never seen anything. The expectation is if you use Coca-Cola red ink and you send it to the device and use it on the surface, it will look like Coca-Cola red. That's all we care about. Yeah. And the proof simulation.
A lot of proofers have their own implementation of the Pantone library with their own alternate colors.
Yeah, that's kind of an important approach that the proofing system have taken so far. They have additional knowledge about Coca-Cola red. So they may have measured, using a spectral measurement device, the Coca-Cola red at 100% and something else. And they may have special built-in algorithms to take advantage of that information. So they might be using spectral data already, but they may also just be using LAB values for the intermediate tint values and then do a better job at simulating the Coca-Cola red. And they have all kinds of custom approaches to that. And some of them are doing a better job and some are not. But PDFX4 has never explained how to do that. The only guarantee you have based on PDFX4 is that if the PDF file says 70% Coca-Cola red, then there should be 70% Coca-Cola red when the plate is being made for the printing process. Or the tone value on the digital device should be 70%. No more. You could have Coca-Cola red with a green appearance. Even Coca-Cola is doing that. Something I never understood. So you do not have green Coca-Cola bottles, but you could make Coca-Cola red in your file and it looks blue. It will not be useful, but it's not wrong syntactically or in terms of the standard. So it's important to see the presence of the spectral data information is not much different in concept from what we had so far in terms of the alternate space for spot colors. Because that was an approximation anyway, and any simulation, especially of intermediate tint values, was an interpolation of some sort. So not that different. In addition, so even if the PDFX6 committee had thought, well, we should do something with it, at the moment there's not a widely known, widely accepted approach about how to use spectral color. It's not that if you take 5 experts and you put them at a table, they would come to the same conclusions. Part of the reason is there's a lot of patents. There's an intellectual property and some want to protect their IP. There's a lot of private source. There's still a lot of research going on, so each of the specialists in this area are still doing research and trying to improve their approach, better modeling and so on. None of them is ready to just share their findings and say, I invite you to learn from my findings and do it in the same fashion. So we are still in an early phase when it comes to spectral color. This may change over time. So maybe 5 years from now, people begin to understand it's more important to be consistent than to be the best. It's always the same challenge. Yeah. If you look at proofing system in the 90s, you had the best proofing systems, and then you had consistency, but this didn't overlap yet. So this is kind of the bits and pieces we should understand and know about spectral data information in PDF 2.0, which is only coming next year, and then in PDF X-6 based on PDF 2.0. I think I have a few minutes left, and I at least wanted to briefly show you something that maybe some of you will fall asleep finally, but just to show you where that information lives.
Can I ask you
Absolutely.
You said it's allowed in PDF X6?
Yeah, it will be allowed.
Yeah, will
Yeah.
be, but nothing else. So there is no guarantee that for all the spot colors you have something in there or nothing like that, right?
To the best of my knowledge, no.
If I understand correctly, these spectral data that you have are based on the material that you've measured them on?
Mm-hmm.
They're dependent on the substrate?
Absolutely, yeah.
There is also nothing that says that the data must be consistent with the output intent of the file or something like that either.
This may be still a subject for discussion in the ISO committee because not many people have thought about it. The problem is, how would you double check? So let's look at some of the data because it will become more clear. But a CXF-X4 file or the data set is just XML text, so you can write down anything. As far as I know, there's no official naming system for substrates. We do have stuff like printing conditions. So if you print according to ISO 12647-2 this year and that paper type, it would probably be FOCRA 51. So we have a language for that in this corner, but there's no language for types of substrates. Some of the other parts are well defined, like the type of measurement device, type of lighting, the angle under which the lighting hits the surface, and so on. But the actual substrate, the best you could put there is a brand name, for example. But even consistency of output of a certain brand may not be very high.
I understand why there's nothing done with it in PDF X6, and like you say, it's not different than what happens today. But consistency between different pieces of information in PFX file has always been a very important thing.
Absolutely.
So that's like the only thing where I would say, well, yeah, but I don't know how to do it either.
Welcome to the club.
Does the spec include actually how you should measure CXF?
Yeah, so the measurement process is relatively well defined. And let's look at the XML a little bit. So so our tool, PDF Toolbox, will have, when it comes out in a few weeks, will have, let me see, will have the possibility to look at CXF data if it is embedded in the PDFX file. And already today, it would be somehow acceptable to put CXF inside a PDFX4 file. And so if you look at the XML for the colorant orange, so in the sample file we just have CXF data for one spot colorant, I think, or do we have several? Yeah, the other ones don't apply. It doesn't work for silver. That's a different story. And it doesn't make a lot of sense for spot white. You could do it, but it will not work. So this is the information, and I will scroll to the end first, because it will become more obvious. So this is the core piece of information in a CXF-X4 file. And so this is a substrate that's very standardized. It's called Steve's substrate. Of course, this is just a demo file. You would have a brand name or something there in most other cases. You have the...
It's a brand, no?
We have the spot ink name, so that's the name you usually use for a certain color. This could be Pantone color or Coca-Cola red or whatever you're using. And then you have an internal, no, this is actually an additional piece of information. This is optional inventory ID. So if you're a big printing plant, you may have to inventorize all your inks, and that's the internal number. This is also optional. You can declare what kind of printing process it is, where you are using the ink, but this is not prescribed. You can have that or drop it. And then you have the set of measurements. So here the background is substrate. That's like the white paper or just the unprinted surface, and you put ink on top of it. And then you have various tint levels, 0%, 10%, and so on, all the way through 100%. And then you have references to the actual measurement data, which I will show in just a second. And then you have the same again for black. So the background is processed black. That's prescribed. You must say processed black, and it should be processed black that you print first, 100% black, and then you print the spot ink patches on top of that. And again, you have references A2, B2 for each of the tint levels to the actual measurement data. And then, let me quickly, where's that? So here's some information about the measurement process. And it's only included once because it's the same process for all patches. So it's a measurement type of spectrum reflectance. So you measure spectrum, part of the spectrum by part of the spectrum across a certain range. It's a certain angle configuration, which is called annular. I don't know exactly what that means, but I know it works. And then the illumination angle, so the angle at which the lighting hits the surface, which is always 45% degrees in this case, and the measurement angle is from the top, so it's 0 degrees. And you start at a wavelength of 380 nanometers in 10 nanometers in increments. And the upper level, I think, is predefined, or there's a default one. It's around 660, I guess. So in 10 nanometer increments, you go from 380 all the way to 660, and you get that number of measurements. And then the actual measurements are further up in the file. So this is the idea that was used for referencing it. This is, I think, 0% of the ink on substrate, so it's just a substrate. And then you get a reflectance value for each of the bits. So at 380 nanometers, there was a reflectance of 0.6851. And the values will vary, so some are pretty high, some are pretty low. Maybe we should use A1, A2, let's go down. So many values. Let's pick something in the middle. So this is, I don't know exactly what it is, but it's kind of in the middle of the tint values. And you see there's some intermediate values like 0.4, 0.5, but there's also higher values like 0.8. And pretty high values towards the higher end of the wavelength. And that should be, if it's, that should be red. Yeah, there should be a lot of red there. And not so much on the other end, like the blue, there's not much. So that's what a CXF-X4 file looks like. So you declare the ink, you declare the substrate, you declare the measurement condition, you indicate which patches you're including. You don't have to have 2 times 11 patches, but it's recommended. You could have as few as 3 patches. But if you're doing a good job, you use those 22 patches.
Where this information is stored in PDF?
That's the next part. So
Metadata, right?
it's a kind of metadata, but I'll show you in a second where it actually lives. So anyway, this is the XML, and you would have such a piece of XML for each and every spot color where you want to use it. So if you have 5 spot colors in your file, you may have 5 XML pieces.
So to predict overprinting behavior of 2 spot colors, is it enough to have measurements of each spot color just over white and black?
You would have to clarify what you mean by enough. But the experts in this field say they have enough information to give you a useful result.
Mm-hmm. So you don't have to measure all combinations of spot colors to get good results.
You could, of course, and then maybe you have a big database of all combinations and you don't need spectral anymore, you can just grab the value. But this is for modeling, so you have a good basic information about the behavior of each spot color, and then you can do a relatively good job at predicting the interaction. And it's a prediction. It could be slightly different. And just to make this very clear where we'll fail, there were two colors listed, silver and white. I mean, white. Would somebody even use 80% white and then mix it with 20% cyan? It would fail for a lot of reasons. Because also the behavior of white is completely different from other printing. It's because the intended goal of white is that it is opaque. It should cover up whatever is below it. The default behavior of most other inks is that they are transparent, so that you can actually mix them. Yeah. The cyan or magenta in the CMYK printing process is highly transparent. That's the reason we can actually use them to combine them and use magenta and yellow and it looks red. It's not just because you may print dots next to each other, they in most cases overlap. And because the inks are transparent, mostly transparent, they will kind of give you a blended color experience. If you use white, it's just not the right ink. Yeah, and it doesn't make any sense to take spectral measurements of 100% white, 50% white, and so on possibly a white substrate. And the same is true for silver. So silver will have to use some pigments that look like silver, some metallic, very small bits and pieces. And that kind of ink is very difficult to print at certain intermediate tint values. So 50% silver, it will, from a printing process point of view, would just not work. You can't print 50% silver. You can print silver or not. And to get a consistent result, you will print 100% silver, but you will not even try to print 50% silver. And it would also be difficult to understand what to expect. So how much is half silver? So it's just not working the same way as the other inks work.
I factored in things like varnishes as well in this, or is it purely ink on the substrate?
I think a varnish would also fail to work. Of course, you can use a varnish in the printing process. I don't know. I would also think that 50% varnish doesn't make a lot of sense, but I don't know.
The solid varnish on a tint range of a spot colour is going to affect it. Of course, that's probably not taken into account here as a separate.
The other problem with spectral data information is it doesn't represent additional information like gloss, which is very important in the appearance of color, or surface. Like, is it rough, a little bit rough? Is it even? Yeah. If it's more even, it will tend to be more glossy. If it's less even, it will tend to be less glossy. If it has a certain type of surface after the printing process, if the light comes from right above or from the side, it can look very different. And spectral measurements fail to capture that.
What part does dot game play in this? Is it counted for, or is it?
Good question. I think, I don't know. I would have to double check.
It's another.
Yeah, it's
another variable in the process.
Yeah.
You're measuring printed patches.
Yeah, but probably not on press. Probably just.
If you want to have,
Yeah.
if you want to do a good job, it should be on the press that you're doing it on.
You would think so.
Just to wrap this up, because the question already came up, if you look at the data structure of a PDF file, like the internal data structure, and I'm using a browsing tool for the data structure here that's built into Acrobat and Callas PDF Toolbox, and other vendors have similar tools. So at the root level of the data structure, you would have your output intents. And I will make this slightly bigger so you can actually see what I'm saying here. So you have an output intent, and this is a PDFX4 file, so we should expect a PDFX4 output intent. And this is the PDFX4 output intent. And I'll scroll up a little bit. So you have the destination profile, which is probably, what is it? Where's the name? Coded Fogra 39, so it's Adobe's profile for Fogra 39. It has some info. Ignore the mixing hints for a second. It has a description of the output condition. It has the output condition identifier, which is Fogra 39. This is prescribed by the PDFX standard. You must have it. Registry name is color.org, the ICC organization. This is also prescribed. It tells the viewer this is a PDFX output intent, not some other type of output intent. And it says, well, I am an output intent. That's the type value. And this is the new entry. So it's yet another entry in the in an output intent that you may have. It's a dictionary, and it has as many entries as you want. And actually, I do have spectral data for silver. I will not look inside; it will just confuse me. And you have a dictionary where you associate the name orange with the XML data. So if I open this, I will just have an XML stream. Very simple, very straightforward, that contains the XML. It's a relatively simple mechanism. You have an extra corner in the output intent, it's called spectral data. You just associate the name of the spot ink with the XML data stream. That's it. And this is the exact same XML as we have just been looking at in the other dialogue.
So this is an array defining 3 spot colors.
It's a dictionary.
Dictionary.
Yeah. Because it's a key value pair construct. So you have the name, orange. You have the value, which is an ASCII string. Okay, that's that part. And just in case you were curious about the mixing hint, there is an alternative approach, and it uses printing order. There's something missing here. Okay. Or maybe not. So mixing hints gives you 2 bits of information, or you could stock 2 bits of information. One is printing order, because it does make a difference which ink gets printed first, at least in conventional printing presses. I'm not so sure anymore about digital. And the other bit that's missing in this case, and it's missing for a reason because we have the spectral information, you could also have solidities for each ink. So solidity implies how much it's transparent. So a very solid ink, silver would be a very solid ink because it's hardly transparent. And if the solidity is relatively low, like for yellow, which is highly transparent, then the solidity value would be relatively low. And this is kind of a poor man's approach to doing what we have just been discussing as spectral data. Because if you have the alternate tint value of a spot color and the solidity, it becomes easier to predict how it interacts with other inks, but only if you know the sequence of inks in the printing process. If silver is highly opaque, but you print it first and then you put black on top of it, you will probably see a lot of black if it sticks. If you print the black first and then the silver, because silver is highly opaque, you'll probably not see much black, because it just covers up the black. So hopefully that mixing hints piece was good enough to confuse you a little bit.
That's also described in PDF X6.
It's described in PDF 2.0.
2.0.
Yeah.
Which means it can be used if it's not explicitly forbidden in X6.
Yes, it can be used along the same lines as I have explained for spectral data. No. Okay, I think I've more than used up my time. There's going to be almost immediately 16:15. Yeah, they have started already probably. There's the final session in the big room in the aula. Thanks for having the patience of staying with me at this late afternoon session, and have some more fun in the large room. Thank you.